Okay. So if you were to look at this vessel of water just directly from the side view, it would look something like this. Well, and I drew a vertical line there. So let's say that's the top of the vessel, and this is where the water is going up to, right? So this is going to be like the water line. Not the whole vessel is full of water yet. So since this cone is facing directly down, then this midsection line is going to be vertical. And since the water is going to be of a horizontal flat top to it, then this should be a 90-degree angle. I also told you that the bottom of this cone, it's a 90-degree right cone, so this angle at the bottom is also going to be a 90-degree angle, but this vertical line splits that angle into two parts. So a half of a 90-degree angle is going to be a 45-degree angle. What would be the measure of that angle here? If this is 90, 45, that has to be also 45. So for a 45, 45, 90 triangle, this side, the long side, that's going to be the hypotenuse, so that's going to be longer than the other two sides. But for these two sides, they actually have to be the same length because they have the same opposite angle. This triangle is going to be symmetric across a line that would go like that. This side has to be the same as that side. And this is going to have length r because it's going from the center of that circle of water to the outside edge of the circle of water, so that's a radius. And if this side and this side have to be the same, well, then the height has to be equal to the radius. That vertical measurement is going to be the height, but it has to be the same as the radius. And so what we can do is now set v is equal to pi r cube over 3 because the h is actually the same as the radius. Yeah, that's a tricky one.
Cubed or r squared?
So it becomes r cubed when you realize that the height is the radius. It would be like pi times r squared times r divided by 3. And r squared times r is r cubed.
So this is like a perfect triangle.
Yeah. Yeah. The 45, 45, 90 triangle has two sides that are the same, and then the hypotenuse, which is longer. When you were in 10th grade in the US, you had to take a class called geometry. And in geometry, they should have told you that for triangles, if you have a larger angle measure for one of the angles, then that corresponds to having a larger side length opposite the angle. So the larger the angle measure, then the more length you have on the opposite side. In our case, with a 45, 45, 90 triangle, since 45 and 45 are the same angle measurements, that means the opposite side lengths have to be the same. Yeah. Okay, let's go ahead and go over the solutions for this quiz. So in question 1, we're given lots of things, sort of rapid fire. Question 1 is kind of like your textbook's version of giving you a related rates problem without having to come up with a fancy word problem. You know, I taught AP Calculus last year to high school seniors, and in the AP Calculus exam, all of their related rates problems always have a really elaborate word story behind them. Like the AP exam will write like a full page about, you know, a lighthouse on a peninsula and ships moving in different directions and blah, blah, blah for related rates. But in your textbook, they like to ask questions like this. So what we're supposed to find is dy dt. And what we're told is that x is equal to 2, y is equal to 1, dx dt is 15/4, and x cubed is equal to 9 times y to the 5th minus 10. And if I'm trying to find dy dt, I notice dy dt doesn't appear anywhere in this equation, but I can make a dy dt appear if I take the derivative of this whole equation with respect to t. So on the left side of the equation where I have x cubed, if I assume x is a function of t, that's going to become 3x squared dx dt. On the right side, if I assume y is a function of t, this is 9 times 5, which is 45, y to the fourth dy dt. And then the negative 10 is just a constant, so in the derivative it goes to 0. So I don't have to worry about it. And now I have an equation. I have an equation where I know all of those values. I know x and I know y and I know dx dt, and I'm trying to find dy dt. So in that equation, I either know it or I'm looking for the value. So you might be able to finish that problem or see where we're going here. That's fine as long as I don't touch it. If you touch it, it falls off. And I can't find a good way to screw that on more securely, so I guess it is what it is. But anyways, x is equal to 2, and so plug that in, and I have 3 times 2 squared times dx dt is 15 fourths equals 45 times y to the fourth, but y is 1, so that's 1 to the fourth power times dy dt. Here on the left side, I've got a 4 where that 2 squared is. 2 squared is just 4. And then I've got divided by 4, so I can cancel those out. I'll cancel the 2 squared with the 4. On the right side, 1 to the fourth power is just 1. So then, after I simplify there, 3 times 15 is 45, equals 45 dy dt. And if I divide both sides by 45, I find that dy dt is just equal to 1. Any questions about how we did question 1 here? Okay. Okay. So moving on to question 2. I'm going to take this expression here for v, the one we found by setting h equals to r, and I'm going to take the derivative with respect to time of both sides. And what I end up with is dv dt on the left, the derivative of v with respect to time, is equal to pi, and r cubed divided by 3 would be 3 times r squared divided by 3. My 3's are going to cancel, and so this is going to be r squared. I'm also going to write dr dt because of the chain rule and because I'm assuming that the radius is changing with time. When I write little r in this problem here, I'm talking about the radius of the surface of the water, right? And so maybe this picture is a little bit misleading. Really, the vessel is a slightly larger cone, and what am I trying to say?
So
Can I erase this?
the picture
No, I
you
can't.
gave us is the water.
Yeah,
Basically.
exactly. That's exactly what I'm trying to say. The picture I gave you is actually just showing you the cone of the volume of water. But sort of the vessel would be a larger cone, right, that has more space above the water as it's filling up. But the water itself in the vessel is going to form a cone itself because it's filling up the cone from bottom to top, and the cone is facing straight down. So yeah, the picture I gave you is actually just the volume of the water. So that little lowercase r is the radius of the surface of the water. So that's the surface of the water. Okay, so anyways, after I took the derivative of both sides with respect to time, dv dt is talking about a change in the volume of water with respect to time. So in other words, dv dt is the rate of change of the volume of water in the vessel as it's changing over time. So the rate at which this volume of water is changing, that's going to be the flow rate of the water entering the vessel, right? And if the water entering the vessel is entering at a rate of 2 gallons per minute, then the volume of water in the vessel is growing at a rate of 2 gallons per minute. So whenever the question asks you to find this volumetric flow rate of water, if we're just talking about the water entering the vessel, this is the change in volume over change in time. And so this is what we're looking for in words. The volumetric flow rate, that is the rate of change of the volume of water over time. That's dv dt. Okay, so this is what we're trying to find is dv dt. We're told that my radius is 2 feet, and the radius is growing at a rate of 1 foot per minute. So if we're talking about a rate that the radius is growing, we're talking about the rate of change of the radius, which is dr dt. So I have r is equal to 2. I have dr dt is equal to 1 foot per minute, according to my problem. And what we're trying to find is dv dt. Then dv dt is going to be equal to pi times 2 squared times 1. So dv dt is equal to pi times 4. And pi is approximately 3.14. And if this were an exam, you would have a calculator. But 14 times 4 is 56. And so this is going to be 12.56-ish. And the units of volume here are going to be cubic feet, and the units of time are minutes. And so this is almost 13 cubic feet per minute. That is the flow rate of the water entering the vessel, which is a pretty rapid flow rate of water. So I know this was a trickier question. Do y'all have any questions about what we did or how we interpreted anything here? So before we move on, let's talk about your exam that you have coming up. That would be exam over 12.4 to 12.6. And I already have on Canvas, I posted the review and the solutions to the review already. So between this class and next class, remember you have your exam on Thursday. Before Thursday, make sure that you attempt the review, try your very best at all these questions, and then look at the review solutions so you can see what you missed and really try to understand those questions before Thursday. But the review looks pretty much how your test looks. There's going to be 11 questions on your test. So you'll have about 7 minutes to answer each question. Some questions are really short and easy. So like, you're going to have to take some derivatives, and I think you should be able to quickly take a lot of these derivatives. Like maybe you'll have a polynomial, so it'll just be the simplest power rule. And then you might have some power function that has a fraction or a rational exponent. And then you might have some product rule. You might have some quotient rule. You might have some chain rule derivatives. Then you'll have two implicit differentiation questions, and they might look something like this. So implicit differentiation is something we covered last Tuesday. And then you're going to have two related rates questions. So they're going to be both word problems, so that's like a related rates question about Netflix, and this is a related rate question about filling up a balloon. The questions are not going to be about Netflix and balloons. They might be a little bit different when you actually get your exam on Thursday, but there will be two related rates questions. And then your last question is what we're talking about today in class, which is just sketching a function as best you can. So you'll have some sort of function like this, and you have to identify y-intercept, x-intercepts, any discontinuities, any minimums, maximums, and inflection points. Try your best to draw it on the xy plane, and then try your best to label all of those things accurately. And so that's what we're going to practice today. Our practice today is sketching curves. And I put together a little procedure that looks maybe a little bit like it says in your textbook, maybe a little bit different. I know I definitely changed a few things when I wrote my notes. But the first step, and probably the easiest, is finding the y-intercept. If your function exists, like if your function is defined at x equals 0, then finding the y-intercept is just plugging in x equals 0 and solving for y. So that should be really easy. Really easy, step 1. Step 2 says find the x-intercepts, and this is always more difficult because you got to plug in y is equal to 0 and then solve your equation for x. You might not be able to do that. Just a heads up. You might not actually be able to do number 2. But you're going to try these steps, and the steps that you can do, that's what you're going to do. Just try your best. Do as much as you can. Steps 3 and 4 are just noticing where the discontinuities are. And remember, if your denominator is 0 for your function, like if you ever try to divide by 0, that makes your function undefined there. So that would be a discontinuity. And also, remember, logarithms don't exist for a 0 input. So if you ever see the input to a logarithm as 0, that's an undefined part of your function. And you can never have a negative input to a logarithm, so that's going to be undefined as well. Step 5, we're going to take the derivative. Step 6, you're going to take the second derivative of whatever you're looking at. And then in step 7, we're going to use that derivative formula and set it equal to 0 to find our critical points. So those values of x that satisfy that equation are going to give us our critical points. And remember that critical points are always either a maximum or a minimum or an inflection point. And so to figure out if your critical points are maximums, minimums, or inflection points, you have to plug those x values in, where you found your critical point, plug those x values into the second derivative, remembering that the second derivative, if the second derivative is positive, that means we're concave up, and you're looking at a minimum. If the second derivative is negative, that means you're concave down, and that means your critical point is a maximum. If your second derivative is 0 at a critical point, that means that you found an inflection point. So that's where an inflection point is where you go from concave up to concave down, or vice versa. Then the last thing we're going to do is we're going to notice if there's any discontinuities in my derivative that aren't actually discontinuities in the original function. And if you have a discontinuity in the derivative, it could be a place where your function is undefined. In that case, it will be a discontinuity of your original function. But you could also have like a pointy point in your derivative, a pointy point in your function. So that way your derivative would be undefined, but your function could be well defined at that point. But that would be something you want to know as you're sketching your function. And then you also might have a point where your function goes vertical instantaneously, just very, very briefly at one point has a vertical tangent line. So your derivative, again, will be undefined, but your function will be well-defined. So you need to know that if you're going to make a good sketch of your graph. So I know that's a lot. 9 steps is way too much to remember, but we're just going to get some practice in, and we're going to try our best. And again, since 9 steps is way too much to remember, if you get to that last question on the exam and you freeze and you can't remember anything, there's something that I call the scrappy method. And the scrappy method of graphing is you just pick out a ton of points for x. And this is the last question on the exam, so if you feel like you've already tried your best on questions 1 through 10, spend the rest of your exam time plugging in more and more values for x. And when you calculate the value for y, that gives you a coordinate pair, and you can plot it on the xy plane and just connect the dots. That's not always going to give you a perfect graph, and it takes a lot more work, but it's super easy to remember, right? Everybody can remember, oh, I'm just going to take a ton of values for x, calculate the value for y, and plot points, connect the dots. Super easy to remember. That's why I call it the scrappy method. If you forget all of the elegant methods that we learn in math class, then you can always resort to, just a bunch of elbow grease. So here's our example 1. We want to sketch this graph of y equals f of x. My first step is I'm going to try to see if I can find a y-intercept. So to find a y-intercept, I'm just going to plug in x is equal to 0. And when I plug in x equals 0, I'm going to get 2 times 0 cubed minus 4 times 0 squared plus 2. And so when x is equal to 0, y is equal to 2. My y-intercept then has to occur at 0, 2, where, remember, I'm writing coordinate pairs as x, y coordinates. That's step 1. It's pretty easy. Step 2, I want to find x-intercepts. And I find x-intercepts by plugging in y equals 0. And if I do that, I get 0 is equal to 2x cubed minus 4x squared plus 2. And you can already see that this is going to be more difficult to find values of x that make this equation equal 0. But we can try. We can have a go at it. I noticed that everything's multiplied by 2 on the right-hand side, but if I were to divide everything by 2, that's really easy to do, right? So let me divide everything by 2. 0 divided by 2 is 0. 2x cubed divided by 2 is x cubed. Negative 4x squared divided by 2 is negative 2x. And then 2 divided by 2 is 1. A little bit easier. Now, maybe you remember this from algebra, maybe you don't. But if you have a situation like this where you have a cubic and there's not really a prescribed formula for getting the roots of a cubic, I mean, there actually is. There is a cubic formula, just like there's a quadratic formula. But it's really, really long, and you won't be able to memorize it. So in this sort of situation, you might look at that plus 1 at the end and think, what are the factor pairs of 1? Or how could I factor 1? And in this case, 1 is super simple. 1 only factors into like 1, like positive 1, or like negative 1 times negative 1. That's the only clean integer factorizations. So maybe I'll just try a wild guess. I'm just going to try x is equal to 1 and see what happens. Well, that would be 1 cubed minus 2 times 1 squared plus 1. And that's going to be 1 minus 2 plus 1, which really does equal 0. And so just by taking a wild guess, setting x equals 1, I found one of the roots of this cubic. So I know that I have one x-intercept at x is equal to 1. That's one of them. So at x is equal to 1, my coordinate pair would be 1, 0 for one of my x-intercepts. Now, again, what I'm about to show you is really only applicable if you remember your algebra class really, really well. But in algebra, you did something called polynomial long division and something called synthetic division. So if you remember synthetic division, that's great. If you don't, that's okay too. You can just skip this part on the exam. But I'll just show you synthetic division, what that looks like. Knowing that x equals 1 is a root means I can put a 1 in this little box. And next to the box on the right, I'm going to write the coefficients of this polynomial. And my x cubed coefficient is 1, because 1x cubed is x cubed. My x squared coefficient is -2. My x coefficient is 0, and my constant is 1. So notice, even though I didn't have an x term, I can't forget about it. I still have to put in a 0. So what I'm going to write over here for synthetic division, you can look this up if you're really curious. What I'm putting out here is 1, -2, 0, 1. The way synthetic division works is you always carry down the first number. So I put a 1 underneath this line, just because that's a 1. Then I say 1 times what I have in the box is equal to 1. So 1 times 1 is 1. Then I say -2 plus 1 is -1. And then I have -1 times 1 is -1. 0 plus -1 is -1. -1 times 1 is -1. And 1 plus -1 is 0. That last number that you write is the remainder of your polynomial after you divide by x minus your root, so x minus 1. If I were to take x cubed minus 2x squared plus 1 and then divide it by x minus 1, what I'm going to get is this right here. But to interpret these numbers, 1, -1, -1, we're going to assign this -1 to be our constant, this -1 to be my x term, and this 1 to be my x squared term. So dividing x cubed minus 2x squared plus 1 divided by x minus 1, the quotient here is x squared minus x minus 1. Again, if you don't remember synthetic division, I wouldn't worry about it personally. I would just get to this point on your exam and be like, oh, well, I guess I can't find any more x-intercepts. That sucks, and move on. But if you do remember synthetic division, this allows you to take your first root and simplify your cubic to a quadratic. And this quadratic is not too bad, because for quadratics, you at least have the quadratic formula. So let me erase this synthetic division bit, and I'll write out the quadratic formula. So quadratic formula says that your roots of your quadratic are going to be -b over 2a plus or minus square root of b squared minus 4ac, also divided by 2a. So in my case, b is a -1, so this will be -1 over 2 times a, which is 2 times 1, plus or minus square root of b squared, which is -1 squared, minus 4 times 1 times -1 for 4ac, all divided by 2 times 1. So -1 is positive, so this is positive 1/2, plus or minus square root of -1 squared is just positive 1. Positive 1 plus 4 is 5 over 2. So it's your two roots are going to be 1/2 plus square root 5 over 2 and 1/2 minus square root 5 over 2. And those gives you your x-intercepts of your curve. So one x-intercept will be x-coordinate 1/2 plus square root 5 over 2. Comma 0, and then another x-intercept is going to be the point 1/2 minus square root 5 over 2, comma 0. And on the exam, you should have a TI-30 calculator where you can take the square root of 5. Square root of 5 should be just a little bit more than 2. And so you can actually get numbers that would help you plot these points on the x-axis for your x-intercepts, right? So that is y-intercepts and x-intercepts. That's steps 1 and 2. Step 3, we want to take note of any discontinuities where I have a 0 in my denominator. But my function does not have any denominator, so I don't have to worry about those kinds of discontinuities. Step 4 says, notice any discontinuities where I'm taking a logarithm of 0 or a logarithm of a negative number, but I also don't have any logarithms here, so I don't have to worry about that step. What do we have next? Step 5 says take the derivative. And so taking the derivative with respect to x here tells me that y prime is going to be 6x squared minus 8x. Step 6 says take my second derivative, which is going to be 12x minus 8. I need to find critical points by setting this first derivative equal to 0. So if I have 6x squared minus 8x equals 0, one of my critical points is going to be an x, because I can factor out an x. And then if I factor out a 2x, I'll be left with 3x minus 4. And so my other critical point is going to be at x is equal to 4/3. So x equals 0, x equals 4/3. Those are going to be my two critical points. Now to find out if these are minimums or maximums, I need to plug in those values I got for my critical points into my y double prime, my second derivative, to figure out their concavity. So y double prime of 0 would be 12 times 0 minus 8. And then y double prime evaluated at 4/3 is going to be 12 times 4/3, which is 16. Minus 8, and 16 minus 8 is positive 8. So since this is a negative second derivative, this is concave down. And since it's concave down, that implies that this is a maximum at x equals 0. Since this second derivative is positive, that means my function is concave up there. And since my function is concave up at a critical point, that means that that is a minimum at x is equal to 4/3. The next thing I want to do, since I know the x value of my maximum and minimum, is I want to know the y value of my maximum and minimum. And so if you have an x value and you want to calculate the y value, that's really easy. In fact, we've already done it for the case when x is equal to 0, because when x is equal to 0, y is 2. So not only is this the y-intercept, but it's also the maximum. The maximum just happens to occur at the y-intercept. It's not always the case, but that's what happened this time. The next thing we need to do is find the y value when I evaluate at 4/3. And that's going to be 2 times 4/3 cube minus 4 times 4/3 squared plus 2. So 4 cube is 64. 3 cube is 27. 4 squared is 16. 3 squared is 9. There's not a lot of simplifying you can do, but you would have a calculator. You would have a TI-30 on your exam, so you could actually plug these values in to your calculator and figure out what is the y coordinate whenever x is equal to 4/3. And so you would have the coordinate pair 4/3, comma, whatever that y value is for your minimum. So I only had two inflection, sorry, restart. I only had 2 critical points, and I found that there were a maximum and a minimum. So that doesn't mean I can't have an inflection point. It's possible that you have an inflection point where you don't have a critical point. If you want to find your candidates for your inflection points, you can set your second derivative equal to 0. So if I set 12x minus 8 equal to 0, I find that I have an inflection point at 8 divided by 12, which is 2/3. So I have an inflection point at x equals 2/3. And you can find the y value for this inflection point the same way. You just have to plug that into y equals 2 times 2/3 cube minus 4 times 2/3 squared plus 2. And use your calculator to figure this out. And that would give you the y value for your inflection point. And the last thing is we might say, are there any discontinuities in the derivative? And in my derivative, I have 6x squared minus 8x, and there's no logarithms and there's no denominator. So that tells me there's no discontinuities. I don't have to worry about step 9 for this one. So we've done a whole lot of talking, and we've carefully evaluated each of these steps. It took us a really long time. Once you get to this point, what you're wanting to do is sketch it. And to sketch a function, you first need to draw yourself a nice xy plane where you can set it up. I want to give myself more space, but I also don't want to erase too much of the work we've been doing. So I'll settle for having a kind of a small xy plane.
We did all of that already? 9 steps already?
Mm-hmm. By the way, on your exam, I'm only going to expect you to sketch this between like x equals -4 and x equals +4. And so for my little plane, I'll mark -4 and +4 as like the highest and lowest bounds of my axes, which means that this is like 2 and this is like 2 and so on. It's 1, 3. Okay. I have my xy plane. Now let's graph this thing. I'll graph it in red so it shows up nice. My y-intercept is that x is equal to 0, y is equal to 2. And this is also, I figured out, that was also a maximum by taking the first and second derivative and finding the critical point with my first derivative and the concave down with my second derivative. I found that was a maximum. Where are my x-intercepts? Well, I have one x-intercept at x equals 1 here, and then I have another one at 1/2 plus something that's just a little bit larger than 1, right? Square root 5 is a little bit larger than 2, because 2 would be square root 4. So 1/2 plus something a little larger than 2 divided by 2 is 1/2 plus a little larger than 1. So 1/2 plus 1 would be 1.5, so something a little bit larger than that, and that is another x-intercept. Then I have an x-intercept at 1/2 minus something a little larger than 1. So this is 1/2, that's 1/2 minus 1. And this is 1/2 minus something a little larger than 1. So those are my x-intercepts that I've plotted on the x-axis. For my y-intercept, I've got my x-intercepts. I also found that I have a minimum at x equals 4/3. So x equals 4/3 is 1 and 1/3. So I have a minimum down here, and I found out that at my minimum, the value is going to be 2 times 64 over 27 minus 4 times 16 over 9 plus 2. Does anybody know what that number is? I see a few calculators in the room. Someone willing to help me? Volunteer your time. I'll box it in red. What are we trying to calculate right here? What is this y value?
Negative 10 over 27 or 0.37 O repeating. Negative 0.37 O repeating.
Negative 0.37 what?
0. Negative 0.370370370.
Oh, I just repeats like that. Okay, so negative 0.37 is enough accuracy for me, right? I can't even sketch with 2 sig figs of accuracy. So that's going to be somewhere around negative 0.4, right? And that should be the y value of my minimum. And so negative 0.4 for a y value looks something like that. And 1 1/3 for my x value looks like there. And that makes sense for my minimum. Okay, I plotted my y-intercept, my x-intercepts, my maximum, my minimum. I also found an inflection point that may or may not be interesting to me. And the inflection point was at x equals 2/3. So here at x equals 2/3, and I'm not even going to bother with the y value. This is also an inflection point. An inflection point. So having plotted my x-intercepts, max, min, inflection point, I'm just going to connect the dots like that. And knowing that I have to remain concave down to the left of my only inflection point, and knowing that I can never cross the x-axis again because I plotted all of my x-intercepts already, I know that this has to just be forever decreasing. Then I hit this maximum, and since it's the maximum, that means I have to turn back around. I can't keep going up, otherwise it wouldn't be the maximum. I'm going to pass through my inflection point where I go from concave down to concave up, through my x-intercepts, through my minimum. I have to turn around at the minimum. I can't keep going down, or otherwise that wouldn't be the minimum. I go back through my x-intercept. And again, on the right of my inflection point, I have to remain concave up, forever going to the right. And so I am forced to just continue increasing forever. And so that's a pretty good sketch of this graph. That's what I would expect on an exam. Again, so I'm going to give you partial credit for this question on Thursday. If you have a good-looking graph, but you didn't label everything, maybe that's 1/3 of the points. If you have a good-looking graph and you labeled your x-intercept and y-intercept, maybe that's 2/3 of the point. If you have a good-looking graph and you labeled your x-intercepts, y-intercepts, maximums, minimums, inflection points, that would get you like all of the points. If your graph looks like garbage, you probably will get 0 points. So try your best. It doesn't have to be perfect, but give it your best shot. This one I think is going to be radically different. So let's take a look at example 2. Number 1 says find the y-intercept if it exists by plugging in x equals 0. So my y-intercept, if I plug in x equals 0 here, then y is equal to 0 minus 1 divided by 0 plus 1. So that's -1 divided by +1, which is just -1. So my y-intercept happens at 0, -1. That's step 1, finding that y-intercept. Usually the easiest step. Step 2 says I want to find x-intercepts if they exist. And so to find x-intercepts, I set y equal to 0. And then I solve the equation 0 is equal to x minus 1 divided by x plus 1. So regardless of whatever the denominator is, my right-hand side can only be 0 if x minus 1 is 0. I can explain that a different way. Let me look at this equation right here and multiply both sides by x plus 1. So on the right side, multiplying times x plus 1 is going to cancel out the denominator. On the left side, if I multiply 0 times x plus 1, it's still 0. 0 times anything is 0. So I say 0 is equal to x minus 1, and that means that x has to be positive 1. That's my only x-intercept. That was step 2. Step 3 says I need to take note of any discontinuities where I have a 0 in my denominator. So what value of x here would give me a 0 in my denominator?
-1.
Yes. -1 plus 1 is 0, and that would give me a 0 in my denominator. So I will have a discontinuity at x equals -1 for sure. I don't see any logarithms, so I don't need step 4. Step 5 wants me to take the derivative. So let's go ahead and try that. Taking the derivative here with respect to x. This is going to give me a first derivative, and I can see this is a quotient rule. I have a quotient of 2 linear polynomials. Now my quotient rule, we'll remember, is this: f prime g minus f g prime divided by g squared, where g is your denominator and f is your numerator. So f prime, the derivative of my numerator, is just 1 times g, which is my denominator, which is x plus 1, minus f, which is my numerator, x minus 1, times g prime, which is the derivative of my denominator, which is 1, divided by my denominator squared, so x plus 1 squared. If I notice that multiplying by 1 doesn't do anything, I can forget about that and forget about that. And I'll distribute that minus sign, so in terms of x's in my numerator, I have x minus x, so 0. And in terms of 1, I have 1 minus -1, or in other words, 1 plus 1, which is 2. So my derivative is going to be 2 divided by x plus 1 squared. That is my first derivative. Now, the whole point of taking the first derivative is to find critical points. And critical points are places where the first derivative is equal to 0. But if your first derivative is 2 divided by some denominator, that can never ever be 0, right? No value of x will give you 0 because you have a 2 in the numerator. If you had a 2 in the denominator, or sorry, restart. If you had a 0 in the denominator, that would make your function undefined, but it won't make it 0. So in any case, there are no critical points based on what I found taking the first derivative.
So we skipped step 4.
Yes, because we didn't see any logarithms.
Okay.
Step 4 is looking for logarithms, and I didn't find any. Let's see. So step 6 says take the second derivative. And the second derivative means I start from the first derivative, and then I take the derivative of that. And I think what I want to do before I even start taking the second derivative is I want to rewrite this first derivative so it's easy for me to understand. I have 2 divided by x plus 1 squared. But if I have a square in the denominator, I can actually move that up to the numerator if I'm willing to make the 2 negative. So I'm going to do this, and I want you to see that it's the same thing. X plus 1 to the -2 power is saying x plus 1 squared, but in the denominator. So these are actually the same. If you remember that negative exponents means you can put it in the denominator and make it positive, then this is the same as that. Okay, now that I've done that, taking the second derivative is super easy. It's just using the derivative power rule and kind of the chain rule, but it's not super necessary. So like 2 stays the same, it's a constant multiplier. Then I multiply by the negative 2, so I bring down the negative 2 from the exponent. And then I have x plus 1 to the power negative 2 minus 1, which is negative 3, times the derivative of my inside function. But the derivative of x plus 1 is just 1. And so my chain rule didn't really change very much at all for me. It just multiplied by 1. And so I can write the second derivative as negative 4 times x plus 1 to the power negative 3. Or like I've been saying, this is the same thing as negative 4 divided by x plus 1 to the 3 power. Because the negative 3 exponent just means you can put it in the denominator, like this. So notice, now my second derivative can also never ever be 0. And if the second derivative is never 0, that also means that there's no inflection points either. There's no place in this graph where you're going to go from concave down to concave up where your function is defined. You can still go from concave down to concave up or vice versa over a discontinuity, but you can't where the function is defined because this second derivative formula does not permit any kind of 0. No matter what value you choose for this x, you can never make the second derivative equal to 0. So we can't have an inflection point. Okay, that covers everything through step 9, really. And step 9 says, take notice of any discontinuities in the derivative. In the derivative, my discontinuity would be x equals negative 1. That was also a discontinuity I identified for my original function. And so I know that that's just a place where I have a discontinuity. I know it's not going to be like a pointy point. I know it's not going to be a vertical tangent line point. I just know it's going to be a discontinuity. So we actually put in a lot of work and we didn't get a whole lot of information out of this one. But I'll try my best to sketch it. And like I said, I'm gonna be looking to give partial credit on this question in the exam. So if you do this work and you do the second derivative, you do the first derivative, even if you find that there's no critical points and no inflection points, I'm still going to give you some credit for having done the work, right? So that doesn't mean don't do the work. It just means, sometimes you try and it comes up with nothing. That's okay. As far as our exam is concerned, I'm still glad you tried, and I'll give you some points for putting in the effort. So here's my xy plane. Again, I really care about what happens between like positive 4 and negative 4 for the purpose of our exam. And I'll mark where the 2's are and then where the 1's and 3's are. Okay, now I'm ready. I have a y-intercept at y equals negative 1. That was the first thing we found. I have an x-intercept at x equals positive 1. That was the next thing we found. And I have a discontinuity at x equals negative 1. This is a discontinuity. And we found that there's no critical points, which means there can be no maximums or minimums. We found that there is no inflection point, at least the inflection point isn't at a place where my function is defined. So there's not going to be that. I'm clearly increasing between this y-intercept and this x-intercept, because there's not going to be a maximum, so I can't have something like that going on. If I did, that would be a maximum, so that can't happen. I can't have any place where this is decreasing like that, because then that would give me a minimum, and I found that there's no maximums or minimums, so I have to be increasing there. I also found that my function is going to be continuous everywhere to the right of x equals -1, because this was my only discontinuity. And I found that there's no inflection point. So my second, I found that there's no critical point, there's no maximum or minimum, so I have to always keep increasing after that. I can't ever decrease again. So if I went from increasing to decreasing, that would be a maximum. Okay, so I have a discontinuity here. And again, this has to be increasing everywhere, because if it ever started decreasing, then that would give me a maximum or a minimum, and I can't have those. So it has to be decreasing, and this has to be increasing. And aside from this discontinuity, I don't really know very much else about my graph, and so maybe I'll pick this point x equals -2 and just plug it in and see what happens. And so if I take my function y equals x minus 1, that would be -2 minus 1, divided by x plus 1, that would be -2 plus 1. And so y is going to be equal to -3 divided by -1, so y will be 3 at this point. And so I'll just plot the point -2, 3. I'm borrowing a little bit of Scrappy method and just choosing an x value and calculating the y value. So my function's way up here on this side of the discontinuity. Okay, let's plug in another point, x equals -3. And so now my y value is -3 minus 1 in the numerator and -3 plus 1 in the denominator. So that would be -4 divided by -2. So y is going to be +2. So right there, -3, +2. So I'm clearly increasing between these 2 points. I can't be decreasing anywhere, because that would give me a maximum or minimum. Can't have those. And then I have this discontinuity where I have to be increasing until I get to the discontinuity, and I have to be increasing getting up to that point. Because again, if I'm ever decreasing, that would give me a maximum or a minimum. I can't have those. So I have this kind of situation here. This is a pretty good graph. I find that my discontinuity has to be a vertical asymptote in order for these points that I found to make any sense at all. And so I guess for this one, in addition to following my steps and learning all I could from steps 1 through 9, I also had to choose points -2 and -3 and just plug them in and be a little bit scrappy with it to figure out what was going on with my graph to the left.